So we were discussing in the previous session Unit 5 of Computer Organization subject, and we had completed Booth algorithm. Today we will start discussing the basic concepts of pipelining from Unit 5 of Computer Organization subject. This is chapter number 8 from your prescribed textbook, Carl V. Hamasher. The contents are also available in Starling's book. So let us start discussing pipelining basic concepts. So when we refer the word pipelining, we know that the purpose of pipelining is to improve the performance, improve the speed of execution. So pipelining involves concurrent instruction execution. Hazards therein are wherever there is a stallment of pipelining, that is a hazard, and hazard leads to degradation in performance. So for pipelining, the machine should be designed in such a way that it should have optimizing compilers, it should have sophisticated compilation techniques. We had seen some way of improved performance with the help of multi-programming concepts and direct memory access. And we know that with the help of direct memory access concept, input output operations and execution go in parallel. No, what exactly is pipelining then? Pipelining is you're organizing the hardware and the execution units in such an effective way that concurrent activity of instruction execution steps like fetch, execute, decode, write occurs. With this improved performance is the resultant. So any program execution involves what? It basically involves a fetch and an execute. What is a fetch? Fetch is we are whatever the program content, instructions and data are there, they need to be brought from the memory for execution. And execution is the actual execution. To understand pipelining, we'll start with understanding two-stage pipelining example by referring the figures 8.1a, 8.1b, 8.1c from the Hamasher textbook, which is an example of two-stage pipelining. Let us look at this example. You can see here this figure 8.1 has 8.1a, 8.1b, 8.1c. And this will give us the basic idea of instruction pipeline. So let us look at the first diagram 8.1a, which is an example of sequential execution. Sequential execution means what? It is not pipelined execution. So let us look at sequential execution. Okay. So any instruction execution involves fetch and execute combinations. So fetch the instruction, execute the instruction. So in a program, there may be multiple instructions. So they may be executed sequentially, like first I1 is executed, then instruction 2 is executed, then instruction 3 is executed. Now, let us say the hardware is organized in this fashion. Post that, how the instruction fetch unit and execution unit are separated. Now you have two separate hardware units for fetch and execute, as well as a interstage buffer called as B1. Interstage buffer called as B1. What we can understand, let us say an instruction is fetched. That fetched instruction will be kept in the buffer B1, and at the same time some other instruction is being executed, and at the same time as this becomes empty, another fetch can be brought. So this facilitates pipelining. Now let us look at diagram C, which is an example of pipelined execution. So any instruction execution, they happen in some clock period cycles. You can see here clock cycle 1, 2, 3, 4, so on and so forth. And you can see the instructions here, instruction 1, 2, 3, like this. So what you can see here is here execute 1 and fetch 2, e1 and f2, you can see here they are going at the same time. And for this combination of hardware is utilized. Say for example, e- execute 1 is being executed in the execution unit. Okay, so at the same time f1 is be already fetched and kept in the buffer b1, and at the same time f2 is being fetched. But if you look at the clock cycle, you can see that at clock cycle 2, two components e1 and f2 are being happening in pipelined process. So this was the example of two-stage pipelining, the hardware required for that. Now we are going to refer figure 8.2a and figure 8.2b for four-stage pipelining. So let us look at this. Now, how many instructions are there? Let us say instruction 1, instruction 2, instruction 3, instruction 4. Okay, and every instruction has four steps here: fetch the instruction, decode the instruction, execute the instruction, write the instruction. So the hardware used for this four-stage pipelining is, you are having three buffers: buffer 1, buffer 2, buffer 3, and this is how your hardware is divided. The components are separate. One for fetch, one for decode, which also indicates decode the instruction, fetch the operands, one for execute operation, one for writing the results. So we need to understand in pipelining what is the role play of cache memory. The role play of cache memory is similar to the role play of cache memory in typical instruction execution. So let us say every fetch we require access to the main memory. So that will cost a lot of elapse and delay, and that will affect the performance of pipelining in such a way that the pipelining concept itself will not be utilized or extracted. So here comes the role play of cache memory. So with cache memory, what is possible is, so we can divide the fetch and other steps into equal time durations. You can select the clock period in such a way that the longest step will be corresponding to the clock period. But still, what may happen is some of the operations like divide may take more time than the allocated clock cycle period. Say, for example, in figure 8.3, which we are going to refer immediately, instruction 2 in cycle 5 and 6, instruction 2 in cycle 5 and 6, at this stage, you can see that W is just doing nothing, W is waiting. So because of that, the buffer 2 is blocked. Buffer 2 is blocked as the contents of buffer 2 are blocked till execute 2 is finished. Till execute 2 is finished. So with this, what may happen is stage 1 and stage 2 are also halted. Uh, with this, what may happen is step D4 and F5 are also postponed. Step D4 and F5 are also postponed. At least you can understand from this diagram that if an operation is allocated some clock cycle period, but it is delaying the allocated time period, that will affect the pipelining operation. That's what it is. And this, you can see here, all the whether it is fetch, decode, execute, right, they are of equal duration and equal clock cycle period are allocated. But you can see the delay here, at least pictorial, that execute 2 is getting delayed a lot. So with this delay, buffer 2 is getting blocked. You can see here with this delay, as execute 2 is delayed, you have nothing to do for W. Then buffer 2 is delayed because of that, as it cannot remove its content till the execute 2 is completed. Because of that, stage 1 and 2 are blocked. So because of that, the steps D4 and F5 are also getting delayed. Now, coming to the word hazard, which we referred initially, we had just now seen there is a delay. In what operation? There is a delay in performing pipelining operation. There is a delay in performing pipelining operation. How this delay is identified? Because every step is allocated some specific clock cycle period. Specific clock cycle period. If it crosses beyond that, then it indicates delay. Then it indicates delay. So, what is the meaning of a hazard then? Any condition that causes the pipeline to stall, that causes the pipeline to stall, is called as a hazard. The hazard can be a data hazard, or the hazard can be a control or a instruction hazard. What is the meaning of a data hazard? It is the non-availability of source or destination operands. What is the meaning of instruction hazard or control hazard? You know that you have heard while discussing cache memory something called as a hit ratio, something called as a hit and miss. What is the meaning of hit? Whatever data is expected, whatever instruction is expected, that is there in the cache, that is a hit. If it is not there in the cache, that is a miss. So if it is a miss, what may happen? That has to be fetched from the main memory. So this will delay. This will delay. So it means what? As the instruction is not available in the cache, it has to be fetched from the main memory. That causes a delay. So that is halting the process of pipelining, stalling the process of pipelining. So this type of hazard is called as control hazard or instruction hazard. So with this, we'll stop here today, and we have concluded the discussion of basic concepts of pipelining. Thank you.